So let us solve a numerical of slab, two-way slab. What is given is the slab of a residential building has a clear span. So clear span is given of size 3 meters by 5 meters, simply supported on all four sides on 230 mm walls, assuming an imposed load of 2 kN per meter square. So this is the live load, and load due to finishes. So floor finishing is given 1 kN per meter square. Design the floor slab. Use M25 concrete and Fe415 steel. Assume mild exposure. The corners are prevented from lifting. So it means that we have to provide the torsional reinforcement. Fine. Let us start with the step 1, that is finding the Ly by Lx ratio to confirm that this is a two-way slab. Even though we can the Ly and Lx are not given exactly, they are not effective spans, but we can use a clear span to decide whether the slab is two-way slab or not. So 5 by 3 is 1.667, which is less than 2, and also it is supported on all four sides. So for two-way slab, the criteria is not only that it should be less than 2, it should also be supported likewise, such that it becomes a two-way slab. Therefore it is a two-way slab. Step 2, we have to decide the trial effective depth, and for that we need to confirm our span to depth ratio. Now Lx is it is 3, okay, so it is less than 3.5, right? So we have this criteria with us that when Lx is less than or equal to 3.5 and or live load is less than 3 kN per meter square, then for HYSD and for simply supported slabs, the span to depth ratio is 35 into 0.8, which is 28. So 3000, that is the short span upon effective depth, is equal to 28 into, this is the assumed modification factor. So effective depth comes out to be 89. Now this 89 is too small, so I will increase it to 100, because I don't think providing a slab of just 8 or 9 centimeter of effective depth, that is really less, right? So it is requiring that much, but we should provide a little bit more, at least in 3 digits, right? So 100 mm I'll provide the effective depth, and total depth will become 100 plus the nominal cover plus 10 mm dia bars I am planning to use, just an assumption. So 10 divided by 2 is 5, so total depth comes out to be 135 mm. Now since we know the effective depth, we can find the effective length using these two criteria that are enlisted in 22.2. So the clear span of the slab is 3000 mm and 230 mm brick walls are there on either sides. So effective span is minimum of two criteria. First is clear span plus effective depth. So 3000 plus 100 is 3100 mm of effective depth, effective length. Second, clear span plus half of support width on both sides. So support width is 230 on both the sides, so half of that, if I add them up, it becomes 230 itself. So 3000 plus 230 is 3230 mm. The minimum of these two would be your Lx. So Lx becomes 3100 mm. Similarly, we can find for Ly, clear span plus effective depth. So 5000 plus 100 is 5100. Second criteria, 5000 plus half of support on both sides, so 230 will become 5230 mm. Minimum of both of them will be 5100 mm. This will give you your effective spans on short as well as long direction. Next, we need to find the loading that is coming on the slab. So load calculations. First, we calculate the dead load. Dead load is capital D, which is 0.135 into 25. This is the density of concrete. So that comes out to be, so I think this comes out to be 3.375 kilonewton per meter square. I guess I made a mistake here. This kilonewton per meter cube, this entire term is kilonewton per meter cube, and that when we multiply by the depth, it will be 3.375 kilonewton per meter square. Floor finish is 1 kilonewton per meter square, it's already given. Live load is 2 kilonewton per meter square, again it's given. When we add them up, we'll get our working load, which is 6.375 kilonewton per meter square. Since we do not work with the working load, we do not design with the working loads, we need the ultimate load or the design load, which is multiplying this by 1.5, so it's 9.5625 kilonewton per meter square. Okay. Now, after load calculations and after we got our ultimate load, we can find the moment that is coming on short span and on long span, and for that we will be using these two formulas, mx and my. Mx is alpha x wu into lx square, and mu is alpha y wu into lx square again. For that we need this alpha x and alpha y. Now our alpha x and alpha y will depend on Ly by Lx ratio. Ly is 5100, Lx is 3100. The ratio comes out to be 1.6452. You will have to interpolate it using this table 27, which is for simply supported slabs, two-way slab, and 1.6452 will lie between value of 1.5 and 1.75, and similarly 2 times you will have to do the interpolation. First is for alpha x, which will be lying between these two values, and alpha y will lie between these two values. So that can be quickly done in the calculator. I had shown the shortcut how to do it in one of my videos. So alpha x comes out to be 0.10922 between these two, and alpha y, it comes out to be 0.04077. So right away when we see alpha x and alpha y, we can understand that mu x is going to be larger because it is attracting more moment. So mu x is 0.10922 into 9.5625, this is wu, into 3.1 square. See, I am taking this in kilonewton per meter, so I have to take the length into meters, the effective length into meters. So this comes out to be 10.0374 kilonewton meter. This is the mu-x. Mu-y similarly 0.04077 into 9.5625 into Lx square again. So it's 3.74697 kilonewton meter. Fine. So we got mu-x and we got mu-y. And now we can find the maximum moment carrying capacity of the slab, and that will depend on the grade of steel used. So yeah, mu max will be 0.138 FCK BD square. This is for Fe 415. So the maximum moment carrying capacity is 0.138 into 25 into B is 1000, because we designed for a 1000 mm strip width into 100 square, which is 34.5, which is way larger than both mu-x and mu-y. Therefore our slab is absolutely safe in bending, and the reason that I write here check for effective depth provided is because if this moment is not greater than these two values, it means your effective depth provided is not enough. You will have to provide, or you will have to revise your effective depth again. That is why I write here check for effective depth provided. So throughout the design, throughout the numerical, we check for depth multiple times. The effective depth has to pass through bending criteria, through shear criteria, deflection criteria, everything it has to pass. Main steel calculation or reinforcement calculation. First we'll calculate the steel along short span, and for that we need 0.5 FCK BDX upon Fy into 1 minus root of 1 minus 4.6 mu-x, this should be x, mu-x, upon FCK B dx square. So first dx is this one, this depth till here. So I will write it down here that this is the steel, x direction steel, and this is y direction steel. Okay, so the effective depth for x direction steel will be your dx, and it is total depth D minus clear cover minus 5x by 2. I am considering a 10 mm dia. So 135 minus 30 minus 5, which gives me 100 mm. This we already know, right? The dx we already know. Dy is capital D minus clear cover minus the dia of x minus half the dia of y. If you saw the moment of y, it is just 3.74697, right? This is a very small or less moment for which we have to design the y direction. So providing 10 mm dia is again too high or too large for y direction. Thus what I have done is I have taken 8 mm dia in y direction, and half of 8 is 4. So dy becomes 91 mm. Okay. So 0.5 FCK B dx upon Fy into 1 minus root of 1 minus 4.6 mu x. That is, this has to be multiplied by 10 raised to 6 because everything is in Newton mm, divided by FCK B dx square. So ASTX comes out to be 292.33 mm square. ASTY 0.5 FCK B dy Fy into 1 minus root of 1 minus 4.6 mu y upon FCK B dy square. So when we substitute the values, we get ASTY is 116.5799 mm square. Now along with this, you have to calculate for two more steels. First is the distribution one, second is the torsion one. Now always remember that distribution steel is also called as minimum steel in slabs, right? For beams, the minimum steel formula was 0.85 ED upon Fy. For slabs, the minimum steel is also called as distribution steel, and its formula is different for different grades of steel. So for Fe250, the distribution steel is 0.15% of the cross sectional area. For HYSD bars, the distribution steel is 0.12% of cross sectional area. So we have HYSD bars and 0.12% of BD, 0.12 into 1000 into 135, it comes out to be 162 mm square. Now as I already told you, this is not just distribution, this is also the minimum steel that is required. If you check the ASTY, it is less than the minimum steel requirement. So you will have to provide ASTY is 162 mm square, right? And wherever distribution steel is required, there also we will have to provide 162 mm square. Okay. Torsional steel, as we know, torsional steel is 3/4 of ASTX, or the maximum 3/4 of the maximum steel. So 3/4 of this one is 219.2475 mm square. Again, this has to be checked with the minimum one, okay? And if this is less than minimum, you have to provide the minimum one. Fine. So we found all four steels, that is ASTX, ASTY, distribution and AST torsion. Now we need to find the spacings for each. So for main steel in short direction, we have spacing of 1000 into pi by 4 into 10 square. This is the area of 1 bar divided by AST required in x direction, 3 times D and 300. So this comes out to be 268.668. We'll round it down to 250 mm. Second 300. According to third also it is 300. So minimum is 250 here. We'll provide 10 mm dia bar at 250 mm center to center. Okay. Now this is the provided thing. We can find AST provided 1000 into pi by 4 into 10 square. This is AST of 1 bar. Upon spacing will give you how much area you are actually providing. So 314.159 mm square is what you are actually providing. 292.333 was what required. Right? This was for shorter direction. Now for the longer direction, 1000 into pi by 4 into 8 square. This is area of 1 bar because we are using 8 mm dia. divided by 162. This is what is required for ASTY. 3 into dy, and last one is 300. So the first criteria comes out to be 310. So you see, even with 8 mm dia, we are getting more than 300. It means that 8 mm dia is also high for this. But do not go lesser than 8 mm dia in slabs. At least you have to give 8 mm dia. 273 mm, and the last one is 300 mm. So we provide 8 mm dia bar at 270 mm center to center. Using this we can find the area provided in y direction. So it is 1000 into pi by 4 into 8 square divided by 270. It gives us 186.168 mm square. So this is what we require in y direction. 162 was required, and 186.168 is what we are providing. Fine. Then we move to the spacing of distribution steel. So for this spacing we have different criteria. First criteria remains the same, that is 1000 into the dia of 1 bar upon the required area. Second is 5 times the diameter, 5 times the effective depth, and third is 450. So first criteria comes out to be 300 mm when we round it down to 300 mm. So we provide 8 mm dia bar at 300 mm center to center for distribution steel. AST provided will be 1000 into pi by 4 8 square upon 300, which is 167.5516. When we come to torsional steel, spacing of torsion steel is 1000 into, I am again taking 8 mm dia for torsion, divided by the AST required for torsion. It is 229.263. We round it down to 220 mm. So we'll provide 8 mm dia bar at 220 mm center to center. I think I should write this down here. Provide 8 mm dia at 220 mm center to center for a mesh of size LX by 5, which is like 3100 by 5. So it comes out to be, I think, a size of 620 mm. Is it? Yeah, I think so. 620 mm. So for a mesh of size of 620 mm, or for a square mesh of size of 620 mm. Okay, this statement you will have to write for torsion steel. Fine. Let us check the slab for shear now. The shear force that is coming on slab, VU is WU LX by 2. So 9.5625 into 3.1 divided by 2 is 14.8218 kilonewton. So this much shear is coming. How much shear can the slab inherently take because of the concrete strength? So that is dependent on K into tau C BD, where K is dependent on the overall depth of the slab. So here in this table of clause 40.2.1.1, it says that for overall depths less than 150, the K will be 130 mm. K will be 1.3. So K, you don't have to interpolate here, that much efforts are saved. So K is 1.3, that is done. Tau C, for that you need PT. PT is 100 AST upon BD. Now this will be AST provided, and that too in X direction, because we are taking we are considering the shear in X direction. Okay, so this is AST provided in X direction, which is 100 into 314.159 upon 1000 into 100. So this is 0.31415. Now it is 0.31415 will lie between these two values, and it is for M25 grade. I'm sorry, it is 0.36 and 0.49. So between these two values are required tau C will lie. When you interpolate, you will get it as 0.3934. Now we just have to put everything into this equation. So 1.3 into 0.3934 into B into D. This will give you your shear carrying capacity of concrete, and as you can see this is far more greater than Vu, therefore the slab is safe in shear. Fine. Now serviceability check. I think this is step 8. So limit state of serviceability and check for deflection. Here we check whether the modification factor that we took in step 2 was correct or not. And for this we'll have to find Fs, which is point F58 Fy area required upon area provided. AST required in x direction was 292.33 mm square. AST provided is 314.159 mm square. So Fs is this formula. When we substitute everything, I get Fs is 223.9752. This when we plot against the percentage PT which we just found in previous step, so no need to find again. When we plot for 0.3141 and this 223, I get modification factor as 1.5 and the one that we had assumed was 1.2. So directly you can say that the slab is safe, but if it is better that we prove it this way, so span upon effective depth, because in that case in step 2 the span that you had taken was not effective span but you had taken 3000, but now we know the effective span, so we have to take it as 3100 mm. So this 3100 divided by 28 into 1.5, it gives us 73.8, which is obviously less than 100, hence our depth is safe in deflection as well. So step 9 is check for development length, and the formula for development length is this one. LD is phi into sigma s upon 4 times tau BD. Phi is the diameter that we are using, which is 10. This is sigma s. Sigma s, that is the stress developed in the steel bar, upon 4 into tau BD. Now how tau BD is taken? 1.4. It is of M25 and it is taken from clause 26.2.1.1. Okay. Now since our steel is HYSD, therefore we can increase this by 60%. So I will multiply this by 1.6 and what I get is 402.958 mm. This is my development length required. Now I have to check it. It should be less than equal to 1.3 times m1 upon v plus L0. m1 is mu by 2. So 10.0374 divided by 2. This was mux basically. So mux by 2 is 5.0187 kilonewton meter. M1 is 5.0187 kilonewton meter. V is the shear force that is coming, so that we already know. L0 is B by 2 minus clear cover plus 3 times phi. I am using 135 degree bend. So this is for 135 degree bend. So L0 is 230 by 2 minus clear cover plus 3 times D is 115 mm. Basically this formula I had explained in my previous video lecture of one-way slab, how this formula comes. So you check that video out if you are not understanding this thing. Okay, so L0 is 115. When we put everything here, let us put it, and yeah, this should be less than D or 12 times the dia. So D is 100 mm and your 12 times dia, 12 times 10 will be 120. So obviously this is not less, so we have to take L0 as 100 mm because we have to take the minimum one. I'll take L0 as 100 mm. Let us put everything in this equation. So 1.3 times m1 upon v plus 100, it comes out to be 540.1833, and now we can say that development length is less than this value, hence it is okay. Hence provided diameter is safe to provide development length. That's it. Now the end thing that we have to do here is we have to detail it, we have to draw everything. So first of all, I'll draw in plan. This is the plan of slab, and this is your clear span of 3000 by 5000. The adjacent thing that you are seeing, these are your brick walls of 230 mm. So these are like 230 mm each on all four sides. Okay, first of all, we'll place our short span main steel. So that it was 10 dia at 250 mm center to center, if you remember. And what we have done here is that alternate bars we have curtailed them, we have bent them up. So like if this is the main steel, I bent it like this. Then the next steel I will bend it from the other side. Then the next steel I will bend it from the other side. So this way we have to bend the alternate bars, and the spacing is 250 mm. This is from center, it is 465 mm till this point, and this much is 310 mm. So from where this came, we'll just see this is actually 0.1 times Lx, and this is 0.15 times Lx. Okay, so 465 is 0.15 times 3100, and this is 0.1 times 3100. Again same from this end. Here this will be 0.65 till this point, and this much will be 310 mm. Okay, 0.1 Lx and 0.15 Lx. Let us draw the main steel in y direction or long span. So that we provided 8 dia at 270 mm center to center. Similarly, here also what we are doing, we are bending them alternately, and these values are 0.1 times 5100, that is Ly, and this is 0.15 times 5100, that is Ly. Okay, same on the other end, the same dimensions. Next, what we have to provide is the distribution bars. Now the distribution bars come here in the edge strip. You remember for two-way slab we have this edge strip and the middle strip concept. So this distribution bars will come at the edge strip, and they were 8 dia at 300 mm center to center. This is a edge strip, again this is a edge strip. Okay, and then at corners, if you remember, we provide the torsional steel. So torsional steel will come, which is 8 dia at 220 mm center to center. So all these spacings we had already calculated, you just have to copy them here. And this diagram is very important for as far as the site is concerned and the construction viewpoint is concerned, because it clears up a lot of things. Okay, so this is about the plan. So let us draw the cross-sectional view of the short span. We first have our tension on the main steel, which is having a distance of 0.1 L, that is 310 mm, and 0.15 L, that is 465 mm. So at 465 mm from the center of the support, we have bent it up, and then this is 0.1 L, right? Same way on the other end as well. Along that, this is your steel in Y direction. Yeah, this is your 10 dia at 250, that is the main steel. This is ASTX. Let me write it as ASTX. This is your 8 dia at 270 mm center to center. This is your ASTY, and this is your distribution. Same way, this is also 8 phi at 300 center to center. This is also your distribution. Okay, the torsional one will not be seen here because they are in the corners. So this was it for two-way slabs, and in the next section we'll be starting with a new topic. Till then, take care. Thank you.